Hello everyone, welcome to this talk. This is a joint work with Li Xun, Xu Yuming, Wang Jingjie, Yang Haochen, Chen Yuheng, Xiao Shujun from National Taiwan University, and Hu Yichun from UIUC. My name is Li Xun. In this talk, I'm going to present our protocol HeadStart, a participatory randomness generation protocol designed for large-scale events. By using HeadStart, people can easily join the randomness generation process and also verify results by mobile phones or laptops in order to ensure the security of the protocol. Generally, a secure randomness should have three properties. The first one is unpredictability, which means the adversary cannot predict the result by observing the generation process. And the second one is bias resistance. That is to say, the adversary cannot manipulate the result to a specific value by changing the inputs of the process. Lastly, the randomness should be verifiable, so that we can mathematically verify a result is indeed unpredictable and bias resistant. Secure randomness is very useful for many applications, such as lotteries, gamings, and fair allocation of limited resources. All of them require secure randomness in order to ensure fairness. In tradition, most of the applications use pseudo random number generators to ensure the participants cannot predict the result. However, because they do not provide an effective way for us to verify, so we cannot ensure there's no misbehavior. Consequently, the adversary can actually craft the input seed to bias the result. Or he can just replace it by a function like listComic, which directly returns a constant value. This function may be hilarious at first glance, but it might not be as far from reality. We can think about the lottery or other systems requiring randomness in our societies. Have we really verified that the lottery machine in front of us or in a live video playing on television does not stealthily put their own malicious get random number function in their system? They might just fool us that the result is totally dependent on random, but there's no way to verify it. Aside from lotteries and gamings, verifiable randomness is very important for public participation, especially for auditing and fair allocation of limited resources. In the past few years, some medical supplies such as vaccines have been relatively limited. Therefore, some countries decide to randomly select the elders or qualified people to get boosted doses. In these cases, people in those countries will really care about whether the allocation process is truly random or not, because the adversary might break the fairness of the process. So, here's a question. If an enterprise or government holds a randomness generation event, can people actively supervise the event holder and also have an effective way to verify the result is truly secure? Accordingly, if there is a participatory randomness generation protocol which allows people to actively contribute their randomness and verify the final results, the participants can truly ensure the result is random, and the event organizer can also prove their honesty. In addition, if all the instructions on the client side can perform efficiently on commodity devices, it will further achieve greater usability and more people can join such a protocol. Specifically, we consider participatory randomness generation protocol should simultaneously achieve security, scalability, and also usability. Aside from security, the protocol should also be scalable when facing a growing number of participants. And you also have to consider the ease of participation and verification efficiency, because the participant might not have the ability to operate powerful servers. As a result, the event organizer should be responsible for performing heavy computations, such as generating a result and providing verifiable security proofs. However, existing protocols are not suitable for these requirements. Some protocols extract randomness sources from Bitcoin or public financial data, but they only achieve unpredictability but not bias resistance, because the sources can still be manipulated. Some protocols adopt commit and reveal schemes, and some others adopt publicly verifiable secret sharing to recover the unrevealed secret. They can hide the input of the random generator before revelation. Thus, they can defend against the adversary who wants to craft the malicious input. However, these protocols still have limited scalability because they require multiple phases of interactions. In addition, Protocols based on PBSs assume that the majority of the nodes in the system are honest, and the reliance on the honest majority also greatly impacts the usability. Because in reality, it is unlikely that most of the participants are patient enough and able to afford the power to complete the protocol. If there's any participant who does not reveal his secret, the honest participant needs to spend their own additional time and resources to recover the missing value. That is very unfair. Therefore, we need to find a solution that can reduce the burden of participation as much as possible to protect the rights of all people. As a result, we propose HeadStart, a participatory randomness protocol that simultaneously achieves security, scalability, and also usability. The random result produced by HeadStart is unpredictable, bias-resistant, and verifiable. Also, HeadStart achieves great scalability because its communication and verification complexity are both big O of log of the number of contributions. Lastly, all the honest participants can efficiently join the protocol and verify the result via mobile phones or laptops. In brief, HeadStart achieves usability because of the ease of participation, verification efficiency, and the most important, the participation do not need to rely on the honesty. Only one honest participation is enough to secure the protocol. In HeadStart, we also define two kinds of role to match requirements in reality. The organizer, who is responsible for generating a result, and the participants who join the event via commodity devices. They can publish messages to an append-only bulletin board providing correct timestamps, and both of them could collude with the adversary. In the threat model of HeadStart, the goal of the adversary is to obtain a verifiable result, which is to his advantage. We construct HeadStart to defend against the adversary, and we assume that at least one participant in the protocol is honest. Now, let's dive into HeadStart to see how it works. HeadStart protocol consists of 4 phases, which are the setup phase, contribution phase, result generation phase, and verification phase. The duration of the result generation phase is slightly longer than the contribution phase. And for example, we assume that the contribution phase starts from April 24th and lasts for a week. In the setup phase, the organizer first initializes all the parameters and functions required in the HeadStart, and then publishes all the settings on the bulletin board, such as the start and the end dates of the event, so that the public can know what exactly is the time they can join the protocol, and when the results should be published. The contribution phase is also the time when participants can register for the event. The participants can submit random strings onto the bulletin board along with the process of registration. By this design, HeadStart allows the participant to freely join the protocol without the need of pre-registration, whereas most of the previous work requires the total number of participants to be a fixed number during the protocol execution. In contrast, our design provides another level of usability in reality. Before entering the next phase, the organizer takes all the contributions as a list of the Merkle tree, and computes the Merkle tree root and audit paths for each participant within a short time. And finally, the organizer needs to publish the Merkle tree root and all the audit paths onto the bulletin board. After the end of the contribution phase, then the organizer can start to generate the result. In the result generation phase, the organizer takes the tree root as an input of a special function called Verifiable delay function. The organizer is responsible for computing the result and publishing the two outputs, Y and Pi, onto the bulletin board. The Y will be the randomness result of HeadStart, and the Pi is the proof of the VDF. By setting the verifiable delay function to take longer than the duration of the contribution phase, we can ensure the result generation phase will be always longer than the contribution phase. As a result, even in the worst case, when the only honest participant present at the start of the contribution phase, the adversary still cannot pre-compute the random result before the end of the contribution phase, because the VDF is set to be longer than the duration of the contribution phase. Therefore, for the adversary, there's no better way than randomly guessing his contribution. Thus, the adversary does not gain any advantage. Finally, after the organizer publishes the results Y and the VDF proof Pi onto the bulletin board, The participant can verify the security of the result via 3 actions. First, they can efficiently check their contribution is correctly included by computing the audit path of the Merkle tree. Second, check whether the tree root is correctly published. And lastly, verify the correctness of the VDF. If all the 3 steps of the verification are passed, then we can ensure the random result is secure. Otherwise, we can show the failed verification process to the others to prove that the random result is invalid. According to the time and space complexity of verification, HeadStart can achieve great scalability even when facing millions of participants. And the verification process can also be performed efficiently on mobile phones and laptops. So far, we have presented the fundamental mechanisms of HeadStart, but there is still one big problem here. Because HeadStart adopts VDF to perform the result generation, and the contribution phase should be long enough to ensure availability for everyone. People need to wait for a relatively long time to receive the final result after the contribution phase. For example, if the event is held for a week, people need to wait for another whole week to get the result, and for the cases such as allocation of medical supplies, the long delay might not be affordable. Some may think that we can just shorten the contribution phase to reduce the delay. However, this shortened contribution phase is ill-suited for public participation events, which often need to last for several days or weeks to ensure fairness and availability for everyone. To resolve this issue, we provide a parameter L that can divide the phases of HeadStart into several stages, and HeadStart will keep propagating the secure access of every stage into the next one. By adopting our HeadStart technique, we can ensure 3 things. First, the security provided by honest contributions can still protect the final result. Second, the contribution phase can still be long enough for public availability. Third, the latency can be tuned to a short time to further improve the usability. For all of these advantages, we only need to spend L times verification of VDFs, which is still very efficient. Furthermore, if we choose to use the VDF supporting a technique called proof aggregation, we can actually reduce the proof size from L times to only 1 proof. Nonetheless, the requirement of this technique is that all the VDFs must be in the same mathematical group. And this is the origin of the problem. Because the most mature implementation of non-trusted setup VDFs is the VDF based on the class group of imaginary quadratic fields. Nevertheless, there's no known efficient implementation that hashes the same group with reduced form. To solve this problem, we designed an algorithm called Clash, which can hash an arbitrary string to the class group of an imaginary quadratic field. By adopting Clash, HeadStart can use the non-trusted setup class group VDF with reduced proof size to increase the performance. In the last part, we briefly present our performance evaluation on several platforms. When the parameter L is set to 100, it only takes 3 seconds to complete the verification on MacBook, and even a 7-year-old iPhone 6 can verify it in 1 minute. That is, if we hold an event where the parameter L is set to be 100, the contribution phase opens for a whole week. It only takes 1.6 hours to produce the final result, instead of another whole week. In our paper, we also presented a detailed security analysis of HeadStart, discussed the extensions and the implementation improvements, and also included some more evaluation results. Please feel free to check out our paper. In conclusion, we present HeadStart to reduce the burden of participation and provide improved scalability and usability in order to make verifiable randomness more popular in our societies. Securing randomness is like taking actions to supervise our government. Passively trusting our rights to them is not a good strategy. Instead, if we want to head for a place having secure randomness, we should start from our own contributions and participation. Thanks for joining this talk. Thanks for coming and have a good day.